So here we are moving on to Einstein. And you've been reading in McClellan and Dorn, you've been reading your chapter on Einstein, his history, his work, his conclusions. And this video is meant to sort of put some of the main ideas into an outline form. So you need to make sure you're reading your text on something particularly like Einstein. You need to also make sure that you have read seen your videos that we have available as well. So Einstein and his theory of relativity, Einstein's special and general relativity. Let's go. Well, I'll try to go. And that may be a good indicator. This is a great cartoon that I thought this is the way to start. The theory of relativity. And this young person is saying, so exciting, but having this scary expression on her face or his face in the process. So it's kind of how I think we all feel when we're addressing Albert Einstein and the theory of relativity. Let's start with a little bit of history. Albert Einstein was born in 1879 and died in 1955. So he's seen some really interesting current events, right, for his own day, not the least of which was the advent of World War I and World War II. He's a theoretical physicist living in the time of extraordinary investment in military weapons, in development of weapons all over the world. And so his expertise was sought out both in World War I and World War II. He's born in Germany. He leaves Germany and is educated in Switzerland. He works in a patent office in Switzerland when he is a young man married with children, so he needs to support himself and his family. And while at work in this patent office, he again had to use great attention to detail in mathematics, engineering, and so his talents were indeed used, but he always longed to be in a university, have a university post where he could work on, again, theoretical physics as opposed to things a little more mundane that he would run across in a patent office. And again, you probably know the patent office was there to issue patents, which basically mean that the country in which they're being issued will recognize that the person submitting an idea or a drawing for a new machine would be able to claim rights to that, property rights to those ideas. So it's an interesting job for a theoretical physicist. So why do we bother studying Einstein? Yes, he makes great contributions to the history of science and to science itself and the way that we think about science. He challenges Newtonian physics. He challenges the way that Newton looked at physics. Newton himself admits that he didn't have all the answers, and so does Einstein. He doesn't have all the answers either. And so by now it should be clear to you that the history of the scientific revolution, the history of science, is one idea building upon another, testing those ideas. So Einstein is going to put some of Newton's ideas to the test. So for example, and I found this quote from a work called Science News for Students. I thought it was a nice one. Before Einstein came along, scientists believed that space always stayed the same. So before Einstein, scientists believed that space was sort of static, and it always stayed the same. Time moved, before Einstein, time moved at a rate that never changed. Before Einstein, time was a constant, and it moved at a rate that never changed. And before Einstein, gravity pulled massive objects toward each other. Apples fell from the trees to the ground because of the Earth's strong pull. Einstein's going to challenge all of these ideas. Let's begin with special relativity. This is a theory of the structure of space-time. The idea that space-time is its own fabric, its own structure. The laws of physics, Einstein says, are the same for all observers in uniform motion relative to one another. So for all of us on the Earth, the laws of physics are the same because we are all in uniform motion relative to one another. No matter if you are watching this video in October in 2018 at a Starbucks, knowing that I made this video in August of 2018 in my office, we still are under the same laws of physics because we are all in uniform motion relative to one another, because we're all on the planet. Now, if you were finishing this class in orbit around the Earth, that would be different. And if you are, please send me a message. The speed of light, the second topic to think about, the speed of light in a vacuum is the same for all observers, regardless of their relative motion, regardless of the motion of the light source. So the speed of light is a constant. The laws of physics are constant so long as all the observers are in uniform motion relative to one another. So they're not an absolute constant. The speed of light, however, is the same for all observers, regardless of their relative motion or the motion of the light source. Other results. Maximum speed is finite. He basically suggests no object or message can travel faster than the speed of light in a vacuum. There is a finite speed. There is a limit to how fast an object or a message can travel. He gives us a very famous equation, E equals mc squared. And in this equation, and we'll talk a little bit more about it, energy and mass are equivalent. Energy and mass are equivalent. He also gives us this concept of time dilation. An object in motion experiences time moving more slowly. So an object in motion experiences time moving more slowly. All right. So let's get a little bit to E equals mc squared. Energy and mass are interchangeable. What does this mean? How do we get to this? Mass increases with speed. This puts a speed limit on how fast things can move in the universe. Simply put, the speed of light, c, a constant, is the fastest velocity at which an object can travel through a vacuum. As an object moves, its mass increases. Near the speed of light, the mass is so high that it reaches infinity and requires infinite energy to move it. Thus, there is a limit, that is the cap, for how fast an object can move. Right? So the idea that there's a speed limit out there, and it is the speed of light, and that is the constant that Einstein identified, offers some very interesting ideas about how to think about motion, planetary motion, how to think about gravity. Yep, so he is going to really set the science world on fire with these ideas. Sometimes it's nice to have the actual equation written out. Energy, E equals mass times the speed of light squared. Right? E equals mass times the speed of light squared. Einstein had discovered, as we noted earlier, that time does not always flow at the same rate. It slows down if you are moving very fast. If you are traveling at high speed in a spaceship, right, any clocks on board or even your pulse rate would slow down compared with your friends back home on Earth. So time does not always flow at the same rate. It slows down if you are moving very fast. The implications of Einstein's most famous theory are profound. If the speed of light is always the same, it means that an astronaut going very fast relative to the Earth will measure the seconds ticking by slower than an earthbound observer will. Time essentially slows down for the astronaut, a phenomenon called space-time dilation. So time slows down. So we've had a little basic introduction to special relativity, but what about general relativity? General relativity is a theory of gravitation. We have special relativity, and Einstein was working on that for quite some time, but what about acceleration? What happens when a mass in motion accelerates? We talked about its maximum speed, but what about during that period of acceleration? Einstein spent 10 years working on the theory of special relativity, trying to include acceleration. The result was his theory of general relativity. General relativity. And this is fascinating for a number of reasons, but basically he suggests that massive objects cause a distortion in space-time, which is felt as gravity. Felt as gravity. From Pedro Ferreira at Oxford, we have Einstein's general theory of relativity is one of the towering achievements of the 20th century. In physics, what we perceive of as gravity actually arises from the curvature of space and time. Einstein proposed that objects such as the Earth and the Sun change the geometry, if you will, of space and time. So you may have seen images like this before. We often think of, because we kind of think of images in two dimensions, we often think of space being sort of flat and objects somehow resting in it. And instead, you may have had the opportunity to have a class with Dr. Huska. There's this idea of you can take a beach towel, if you will, and put a bowling ball in it. And that really is what is a nice representation of this curvature of space-time that happens. Einstein showed that the way mass alters space, right? So it's the way that mass alters space makes bodies move as if they were pulling upon each other, just as Newton had described. So Einstein's theory was a different way of describing gravity, but it was also a more accurate way to describe gravity than Newton had made in the past. So although the Earth appears to be pulled towards the Sun by gravity, there's really no such force. I know, we used to think we could all count on gravity. Sorry. So even though the Earth appears to be pulled towards the Sun by gravity, there's really no such force. It's simply the geometry of space-time around the Sun telling the Earth what to do. In the presence of matter and energy, the curvature of space-time can evolve. It can stretch, it can warp, form ridges, mountains, valleys. This causes bodies moving through it to zigzag and curve. We have other examples to consider when you're thinking about Einstein's theory of relativity. For example, a lot of us rely upon GPS, whether it's for our cell phones or what have you. And GPS or satellite atomic clocks click faster than atomic clocks on the Earth because clocks in space experience a weaker gravity, a weaker pull than clocks on Earth. The GPS clocks are moving faster relative to the clocks on Earth, right? This is bad if you want to try to triangulate things. This is bad if you want to have a satellite determining the location of your cell phone, right? GPS clocks must be made to tick slower than earthbound clocks if GPS triangulation is to work. So a GPS satellite clock second is longer than a clock second on Earth. Right? Okay. The difference is really real. If no relativistic effects were accounted for, if you just let a GPS atomic clock go the way that a satellite clock go the same as a clock on Earth, a GPS unit that tells you it's a half mile to the next gas station, right, would be, if it wasn't fixed, tomorrow that gas station would be 5 miles away. Or at least it would tell you that. Yeah? So the difference is real. If no relativistic effects were accounted for, a GPS unit that tells you it's a half mile to the next gas station would be 5 miles off after only 1 day of fast-moving seconds. A very famous experiment that needed to be done to help Einstein prove some elements of his theory relates to the total eclipse of the sun. You have that in your video. from National Geographic. You certainly have this in your McClellan and Dorn. And this image is nice. First off, you get a nice representation over here on the slide of what Einstein was hoping to accomplish in 1919. But here you have the sun, right? Here you have the moon. Here's the observer on Earth, right? Watching the eclipse with protection, thank you, over your eyes. And as the moon blocks the direct sunlight between yourself and the sun, right, the sky becomes dark. And sometimes you can actually see starlight, right? And what Einstein was hoping to do was to get a photograph of that starlight, because here is the true position of the star, right? Here's the eclipse happening. But as the observer on Earth, you see the starlight coming from here, because you're assuming that that star that's producing that light is straight ahead. It's right out there in space. When in reality, according to Einstein's calculations, that star is actually here, right? And as the light comes around that space-time fabric that's created, those curves, etc., because of the mass of the sun, here you go, we're going to go around it and we're going to bend light. Light actually bends. And it bends because the fabric of space-time bends and curves. It makes mountains and ridges and valleys, right? So, this test of general relativity, this demonstration of the eclipse, and taking photographs of that eclipse to demonstrate how the light that works around that eclipse was something important to proving Einstein's calculations. So some basic results. We've talked about several things in class, in your readings, in the videos you're watching. But rays of light bend in the presence of a gravitational field. Light bends. That's important if you're trying to calculate the location of stars, right? The universe is expanding. Another result of Einstein's theory. Especially important for those who are trying to understand the origins of our universe. If our universe is expanding, what's it expanding from? Right? So, a very interesting theory, a very interesting and important contribution to the history of science. And please continue to work on this problem of Einstein and his contribution. And if you have any questions at all, please holler, please call. If I can't answer them, we'll find somebody who can. Thank you.